cover crop emergence mapping for crop condition monitoring, and also I'm talking about cover crop termination detection for agroecosystem assessment service. Move to the next slide. Okay. First, we want to make sure that's crop growth stages. So first, we want to clarify this crop phenology and growth stages and remote sensing phenology. There are two different concepts. So the crop phenology defines the physiological development stages of crop growth from planting to harvest. It's normally observed from field. And remote sensing phenology, or sometimes people call the land surface phenology, RSP, it's kind of inflection point detected using time series, normally from vegetation indices. They are associated with the change of the green vegetation coverage and conditions, such as like growing up, maturity, senescence, dormancy. So remote sensing phenology, or RSP, have a different relationship to the crop growth stages. They need to be like correlated, linked to the crop growth stages for the application. Many like remote sensing phenology methods have been developed in past decades. If we look at the data used or the production days, we can see this can be categorized into two categories, those approach. So one is like after season approach, one is the within season approach. So after season approach normally produce the data 6 to 12 months or 1 year after the vegetation growing season. So it's used the prepended and appended remote sensing data. For example, modest phenology product uses 3 years of the data, like 1 year before and 1 year after, to map the crop vegetation phenology, or RSP, for the middle year. And various and HS data use 2 years of time series that's added in, and 6 months before and after their target year. Normally, you need to cover a complete cycle of vegetation growth. Within season approaches use the latest available remote sensing observation to produce land surface phenology. It can use any period of time series data. Since the within season approach can run anytime using the latest observations, they are also called the near real-time approaches. So there are different definitions on the near real-time, I would say. For the agriculture statistics, weekly report can be regarded near real-time monitoring. We probably don't target to hourly or even minutes monitoring. So this presentation probably more focused on the weekly or daily. So within season approach also aims at a specific crop growth stages. For this presentation, I'm going to cover the crop emergence and cover crop termination detection. Just a brief review of the after-season phenology mapping method, just in case you are not familiar with the land surface phenology using remote sensing. There are different approaches. One is like a curvature-based approach, looks like such as the modest collection 5 and a various phenology algorithm developed by Xiaoyang Zhang and Mark Friedel. They're looking for the curvature, the changing point, the maximum curvature point, and to find the green up date, senescent date, or dormancy date. And threshold-based approach, such as a time set, many people are familiar with this toolkit package, software package. Modest collection 6 and harmonious Landsat Sentinel 2 phenology product actually use this kind of approach. So the basic idea is you get the minimum maximum value, and you know the amplitude between the mean and the maximum value. and define a threshold, a percent of threshold of the amplitude to find the growing up date, mid-growing season, or the peak time. There is another approach, category approach, is called shift-based approach. It's mostly used for the crop phenology detection. It relies on the reference from previous years, and also you need to know the crop types from current year, and plus some observation from this year. Then use this reference curve to fit into the current year, so you can estimate the individual each crop growth stages. Those are mostly work like after season approach, but some can be extended to the within season approach. So within season approach, first of all, I want to show the within season approach for crop emergence mapping. Those after season approach are quite useful for retroactive study, but for the operational application, we need to map the crop emergence as soon as possible for early crop monitoring, because this crop emergence is a critical stage for crop development and crop growth modeling. A lot of time we cannot get these dates because farmers may decide their planting date differently from year to year and from field to field. It's quite a challenge actually map the crop emergence in near real time. As you can see from this plot, is emergence time for corn and soybean. Those are small change in terms of the background, soil or crop residues. So early detection may be affected by those soil type and soil moisture when we only have limited data. We developed an algorithm called within season emergence, or WISE algorithm. It's a kind of a trend-based approach. Every time we look at the crop growth stages, it represents a change of management of growth status. And remote sensing phenology has to be associated with this change. So the one question is like, what's the change in remote sensing? So every day we can say it's different from other days, and the remote sensing data changed or surface condition changed. But we are only interested in those more substantial changes in remote sensing that can be associated with a meaningful event. So we use the two rules in change detection. One is we want to detect the meaningful change, and the second is what's the substantial of this change. In this algorithm, we adopted like moving average convergence divergence approach to identify the shift of the data. So this MACD, or called MACD, is quite normal index to identify bull or bear market. So we define the strength of the trend. Normally, detect MACD can detect the increased trend after it's happened. So we define we revise this algorithm to detect the early detection change data. It's called WISE algorithm here. So not only to detect the date, we also detect the increase of the momentum, like the cumulative MACD value after MACD become positive. So we call it momentum. So it's very important index in the later presentation, because we depend on this data to identify the significance of the change or the emergent state. An example from a cornfield near our research area. So we, as you can see, we have a very limited observation until to the mid-June. And in this time series, this is dot is Venus data. Venus is experiment mission by France and Israel. So this is a 2 days repeat, but there's a lot of cloud, of course, in the winter time and the snow. Well, in this time series, we can fit into this time series and identify two growing up dates. The first growing up date is actually associated with the width, and the second is actually the growing up data for the coin. Because we don't have a lot of observation right after this actual emergence. This is actual emergence data and planting data for this field. We are not really confident on these cases. So if we look at the momentum for the width is 0.008, and then the new detection of coin emergence is 0.003. It's actually weak than the width. So even though we can identify this point, we are not really confident on this detection. Then when we get more observations until the end of or middle of June, get much more confident, like it's increased, and we can see the momentum increase to 0.035. So this approach not only detect the emergence data, we also can give the confidence of this detection. That's kind of nature of the near real-time monitoring. Once we get more observations, we are more confident. I want to choose this example because this is a quite challenging example for any algorithm. You have multiple growing up dates from our alfalfa field. This is also very close to our research area. So they have multiple harvest event and regrown. So each time we can capture this new growing up dates. This is an interesting plot because we don't have not only have the Venus data here, the solid line, you can see this is Venus observation as I mentioned before. And we also include the planet data. And as you know, but planet is a small satellite constellation, include like 100, I think right now it's 150 satellite in the orbit. So they can provide a daily observation at a 3-meter resolution at a global scale. So I include the planet data here. So even though this data are a little different from Venus data because their sensors are different and acquisition strategy are different, the time series are quite different, but the detected growing up dates are similar. So that's a good sign for the high temporal and spatial resolution data when we use this data set. This is a near real-time simulation. So we did this simulation using the Venus time series. This slide shows the growing up data detected using Venus NDVI time series from January 1st to June 15, and from January 1st to July 1st, and then until July 15. So for first June figures, that's the only data we have until the June 15. So we can detect 1, 2, 3, 4, 5 fields, the growing up date. And once we get the additional half months of data, we detect 2 additional coin field, the growing up date. And until the July 15, we can identify emergence field or growing up field for almost all the field in our area. This is a Bellsville Agricultural Research Center area. And you can see the added figures, and the C means the coin, and S use S for soybean. And then we can compare to the actual field observation, and those I use compare the different vegetation indices. This example shows the EVI2, NDVI, NDVI red edge band. All of them get a very good result and very high correlation. And NDVI is not really bad compared to the EVI2 or NDVI red edge band, because that's very popular, most commonly used or historically used vegetation indices. So we use the NDVI in here, and it can be saturated in the peak growing season, but the emergence data, because that's very low vegetation coverage, so NDVI saturation is not a problem for this study. And you can see the mean difference mostly like within 3 days, and we can detect the this crop emergence within 1 to 2 weeks after actual field emerge. And before I mentioned this data like Venus data experiment data set, planet data it's a commercial data set. So if we want to apply to a large area like in this multiple state, we use the harmonized Landsat Sentinel data, which is freely available from LP deck. We extended this WISE and HS data to 5 coin-based states here, including Iowa, Illinois, Indiana, Minnesota, and Nebraska. It's include 9 actual agriculture districts in Iowa and 13 unique phenocamera sites. Those phenocamera sites, and also those phenocamera sites provide multiple years of observation. So we have 34 site-year observations I can compare. And this map is from 2020 cropland data layer from NAS. First, we want to assess the WISE agronom and HS data using phenocamera observation. Those are 34 phenocamera sites. We find most of them agree well, but they're like a C3 coin being coin, number 1, soybean number 1. But we also found some lead detection like coin 2, soybean 2 fields, and also 2 coin soil field from WISE agronom. And I'm going to check those fields individually in the next slide. And the mean WISE like 3 days and MAD mean absolute difference is within 1 week, and we get R square 0.72. You can see, we want to look at the individual field with the phenocamera information, and those GCC value from phenocamera. It's R is green divided by RGB signal, and you can see the first one agrees with HS very well. But you just need to look at phenocamera. You normally look at alternator, and maybe look at different area. So we expect some difference, but this case looks really good. So we can identify similar growing update. And this case is also a good case. And this is a cover crop, actually, in growing a cover crop, and then regrows growing up from a cash crop or summer crop. So we can identify this case. This is the ideal case actually for the agronom, because this shows a trend change. It's more challenging, you have flat area and then increase. So there's some, like this case, they have large uncertainty from remote sensing detection. So we look at compare the agronom to the actual phenocamera site from multiple years, and then apply this agronom to the entire area. So this is 30-meter resolution growing updates from 5 states in 2018. We used the image from January 1st to August 16th, so that's still within season approach. We didn't include a 4-season image. Those black color shows indicate that growing update cannot be detected. Sometimes those are no strong growing up signal, sometimes because of lack of the clear observation. And this is the growing update from 2019 for same area, and we run through the 2020. As you can see, it's from year to year, there's some inter-annual variation here. And if I put them together, it's Illinois, just pick them Illinois. Illinois actually has the highest degree of inter-annual variability in crop emergence. This is in agree with the reported emergence state. We detect the crop emergence earliest in 2018 and the latest 2019, particularly in the northern Illinois. So that was related to the historical cool and wet weather in 2019. Some fields in 2019 were not planted at all. So according to the USDA Farm Service Agency, the crop average reported by Illinois has the largest amount of prevented planting area among 5 states. So that's kind of the information confirmed that remote sensing detects this kind of a delayed planting and emergence state. As you know, that some NASA has a crop progress report. They include the crop emergence data, but they provide the state level assessment. This plot is a cumulative percentage of the crop emergence. This shooting dashed line from NAS crop progress report. And green update from remote sensing are showing a solid color. We can see that's especially for these two, Illinois and Indiana, they have very different emergence data and the planting data from in the area from 2018 to 2020. So we can identify this trend based on the remote sensing. There are, I want to say, there are differences because we are not to look at the same area. Sometimes like NAS has a sampling site, and remote sensing is based on pixel, probably more coverage of reflect the entire state. But the good thing is we can provide 30-meter resolution, and so it's for the this area is like our field scale, and then we can compare the NAS report to the remote sensing detection using a medium data. This is previously actually this is a accumulative histogram, so we pick up a 50% point as a comparison for the crop emergence between the NAS report and remote sensing estimation. You can see that's a pretty good agreement from here. The bias almost just less than 2 days in the medium data. RMC less than 5 days. It can be applied to the other area to give us more confidence apply to other area. And the second topic I want to talk is the cover crop termination mapping. It's also within season approach, near real-time approach using remote sensing dense time series. Cover cropping are planted during the off season. Normally in the fall time going through the winter. It's used to protect the soil and improve watershed management. The Maryland and Delaware, that's the eastern shore of United States. They have the winter cover crop cost share program. So use the cover crop planting data and termination data to determine incentive payment. So the government, the Department of Agriculture from Maryland and Delaware, they pay the farmers to plant cover crop to protect soil and improve watershed management. But in order to decide the payment, they have a very specific regulation. Like it need to be termination must be between the March 1st and June 14th. That's in the 2020 agreement. And they have a eligible additional payment, incentive payment after May 1st because they can get a higher biomass to encourage the take the extra nutrition, protect the soil. Those planting data and termination normally collected and confirmed by the staff from those departments for each enrolled field. As you can see, this verification is kind of the intense, labor intensive and time consuming, and it to be available like in a short time. It become very restrictive in the COVID time. And so the department asked us if remote sensing can provide any estimation. So we try to use the high temporal remote sensing data to detect this cover crop termination dates and provide this information to the department so they can decide if it's terminated or when it's terminated, how should they make this payment. So the approach is pretty similar to the previous one called WISE algorithm. I call this WISE algorithm. It's a termination algorithm. Also, it's a trend-based algorithm. Those are determined by first we look at the downward trend instead of increase. Emergency is looking for the increase, but termination is like a decrease trend. We look at this or called the senescent period from a time series using similar MACD index. And we're not looking at the point, we're also looking at the magnitude what's the mean value and the maximum during this decrease. So that's the amplitude. And also look at the downward momentum, that's integral value of MACD. So these two indexes will be included in the delivery, like this detection. This is the actual harvest date, and this is our detected date. We not only provide detected, we also provide the confidence or this amplitude and downward momentum for together with this delivery. And we look at the actual data was determined by the two observations actually during this senescent period. These two observations will show the most rapid rate of decrease of VI during the period because the cover crop termination normally terminated when the cover crop are green. So the change in the VI is abrupt. It's a quick change. And the uncertainty is between these two days, actual observation date. Again, I want to use this alfalfa as an example because that's a challenging case. If I would say if your phenology agronom new film works for alfalfa field, it probably works for a lot of different fields. Is this one season from spring to the fall? We can see the 4 cycles here. So each cycle we detect this vertical lines, those are actual harvest date, and the red dots the remote sensing detect termination date. And in this case, we did a very good job in identifying 4 harvest events for this alfalfa field. Okay, and the previous research, like agronom, was developed based on the Venus data. It's very experiment data set. But if we want to extend this approach to the large area, we use the harmonious lens and Sentinel-2 data, which is 30-meter resolution, 2 to 3 days repeat. And as you can see, this is a HRS data for 2 cover crop field in Eastern Shore, Maryland. And the first one, it's planted from here, the cover crop planted from here. It started growing up in the 4th season, but until the winter time, it's actual decrease of the NDVI. And then when spring comes, a pickup the growing up and then terminated. And then the summer crop, cash crop start to plant. So we want to identify this point. That's the decrease point. This is the actual vertical line, is the actual reported termination data, and the squares are detected from sensing. And another case is similar, like planted and grown, and the decrease of due to the winter time when the temperature or snow. Then in springtime, it's pick up quickly. It's much faster than this one. So both cases we can detect, but this case we have less confidence. So it's associated if we look at the NDVI amplitude is only 0.16 and momentum quite small, 0.6006. And this case, we have NDVI amplitude 0.58. That's a big decrease, like from a top to the medium, high to the medium, to max to the minimum value. And MACD momentum also high. So we can get a higher confidence on this detection. We can detect the small change, but probably less confident. And then we do the assessment using roadside survey, and basically driving a car in the road and take a picture on the right side of the field. This is not terminated, and this terminated because we are driving those truck on one day, so we can only identify like a terminated or not terminated. We don't know actually which day terminated. And we drive 3 days and we compare, run through the agronom. Like we have a 300, almost 400 point photos, and we can detect 330, for about 80% can be detected. Some cannot be detected probably because of the weak signal or the lack of the clear observation. Among these detected, we can detect correctly the terminated, not terminated. 95% can be detected correctly. But if you compare to the total number of photos, we can detect 79% because there are some fields we cannot be detected by the agronom. And We also compare to the reported data because farmers also report their own termination date. That's maybe different from remote sensing, but in the past, they just accept this farmer reported data and do some verification. And we can compare to their database. We have, I think, a few thousand, 2,000, or more than those fields we can compare. And this is a difference between the HRS detection data from MDA data, Maryland Department of Agriculture, that's in weeks. So we found like 48.6, 71.8, 84.2, and 90% of detected field were within 1 to 3, 4 weeks of agreement in 2020 to 2021 season. And if the Maryland can accept like the difference within 2 weeks, so 70%, 71% have very good agreement. They don't need to visit the field, and also determined by the magnitude or our competence level. So that saves a lot of their time. They only need to focus on 30% probably disagreement. A lot of time, I would say, remote sensing probably are correct. And this shows the idea of the near real-time processing. And we run like 10 simulation every 2 weeks here. This is 10 bi-weekly simulation. So in the initial time, like we start from March 18, we can detect one small termination. That's very small signal here. So that's probably not reliable. So after April 15, we can detect the termination date from our later run with the same data from here. And this is a reported, the vertical, those are reported termination date. We are a little bit different from here. I think the farmer probably reported the termination date when the total, the field becomes no green on the field. They call that for a termination date. We detect the first signal when it's become less green. So I think both are probably reasonable. That depends on when they report. And then we develop a system to support this agroecosystem assessment. So it's called near real-time monitoring for winter cover crop using harmonized Landsat and Sentinel-2. We have the Landsat HRS data. You can download this data from LP deck. I said it's I think the latency time probably only 3 days, 3 to 4 days. They are doing a good job to harmonize Landsat and Sentinel-2, make them consistent radiometrically and geometrically, and in the 30-meter resolution data. And they provide a better, much better cloud mask, I think, than Sentinel-2 data product. We have enrolled field polygons. Those are reported, enrolled by farmers. And we also have the report. So we run through the waste algorithm. We have 2 modes. One's image mode, it processes individual pixels. So we can make the winter cover crop termination map. And we also can aggregate this field data, generate an NDVI time series for the enrolled field. That's a text file. So we can run through the algorithm to generate this termination data for the enrolled field, because that's what they are really need from Department of Agriculture in Maryland and Delaware. We can assess using their database and improve the algorithm. So it's operational, semi-operational, I think, probably for this agroecosystem assessment. We deliver the data every 2 weeks or during the springtime for the last 3 years. They found it's to save there a lot of time to visit the individual field. I would say the remote sensing probably cannot do 100%, but I think so we can save like this, as this case, we probably can say 70% agreement and very confident, high confidence. So they don't need to focus on this 70%. They can work on an additional 30% from field. So this plot shows the data of termination date from 2021 to 2020 to 21 period, growing period, over Maryland, Delaware. This is called the Amava Peninsula. So most termination date, we do the histogram of this termination date. Most termination date happens in the week 15 to week 20. That's approximately to the mid-April to late May. It's very similar to the in-road field, those blue line. So the summary, so near real-time crop phenology mapping is feasible, as I demonstrated in this presentation. We have two cases. One is we use HS data to detect the cover crop emergence, and one is crop termination. Both are successful in our area. You can see that's a 2 to 3 days repeat, quite good. And the trend-based approach can capture this crop emergence and cover crop termination. Of course, this just use we just show the detecting for the specific crop growth stages. So not all the crop growth stage can be detected using near real-time remote sensing data alone, because sometimes those crop stages change, maybe not really strong signaling in the remote sensing time series, especially during the peak growing season. You don't see the change, a lot of change in the VI. So additional information, I think, may be needed to improve this crop phenology and detection. We are developing a new algorithm to map the entire crop growth stages using historical data. So the weather data will be useful. Historical crop growth information will be useful, and also the basic idea on the crop calendar when the usual planting data will be useful. I think that's and also if you have the crop management information can help the algorithm. But sometimes those information are really hard to obtain from even from a field or from management. They don't record. But that kind of those information. So with that, I'm just end this presentation. We can, if you have any question, you can type it in the chat, or you can unmute your Zoom. So I can take a question right now.
Okay. Thank you for your nice presentation. Is there a question? First of all, I have a question. Have you had any special investigation or performance measure dedicated to, for example, winter wheat? How many of the phenological stages do you guess you can monitor or detect through remote sensing? For example, usually we say that although there are 8 defined phenological stages in yield estimation, irrigation management, and such processes, usually 3 main segments, minimum, up to 5 segments, are useful as a balance between the computational feasibility and the observational availability. And what's your opinion about their probable usage for winter wheat or other cereals? Which will be the feasible range, and how many of the stages would be available through the method that you propose if we aggregate it with some local additional measurements?
Yeah, that's good. That's a good question. Actually, this research is still focused on specific stages. Right now, we can do the emergence, crop emergence. For the winter cover crop, we can do the crop emergence, and so that's probably similar to the winter wheat, because that's also include the winter wheat. So once we know the emergence state, we probably need to. It's not focused on the other stages yet, but I think the other stage, crop growth stage, need to be need additional information from previous observation. Like you have a reference curve from past years, then you know the those stages associated with this different curve. So that's kind of combined, you have a time series, and then combine the different stages and then fit into this year. that's kind of ongoing study. I think there are some study already performed on this mapping, and they basically use the shift-based approach. Like you have a knowledge, previous knowledge on the growth stages and the time series, and then fit into the current year. You can map, but I have not studied that yet. We are working on that topic, and I think there's some. It's possible to do the near real-time monitoring and probably very short time prediction. Few days prediction probably should be fine.
Okay, thank
But
you.
this is just to focus on the emergence and termination.
Another question is, if the terrestrial data is unavailable, but you have registered fields, that means you know the type of crop there as a pattern. Will, for example, hyperspectral data be an additional parameter that can help better investigation of the current status of the phenological stage?
Yeah, that's possible. Yeah, that's possible. So we can look at different indices and look at red edge band, like NDVI use a red edge band. It shows some improvement. But since we use the operational application, we use the Harman's Landsat and SAM2. Landsat don't have the red edge band yet, so we just use a standard NDVI. It could be better, like if you are hyperspectral or other bands.
Okay. And there is a question in the chat. How do you separate the effects of factors such as meteorology, topography, farmer behavior, local seasonal trends, among others? Abdul White is asking.
Okay, no, this we have not considered this fact. This is just in fact reflecting the remote sensing. We think it's if you have different planting data, different behavior, that should be seen from change of the time series. Some like a different field, you have a different planting date, then the NDVI increase time will be different. So that's also detected from remote sensing. We don't need to actually know the ground condition before we're using the remote sensing time series analysis. It's a trend-based analysis.
Yeah, regarding to my experience, phenological stage-based data segmentation is crucial, especially for large-scale observation and agricultural management, basin management, and so on. And I have a personal question. How is the usage or its point of view from USDA, US Department of Agriculture, in evaluation of yield monitoring, yield reports, and so on? Is it a part of your strategic roadmap for improvements of the local and international observations?
We are the research unit. We develop approach, and then if we have other agency, NAS, like Agriculture Statistics Service, they probably more focus on a large area. We also have a foreign agriculture service. They probably work on the international side. NAS more work on the US in the US. So we are like a research side. We research agency. We support their other agencies. We don't involve directly in the large scale yield mapping or yield estimation. So like we have a very good connection with NASA. If we develop some ever new algorithms, they can adopt this algorithm into their operation application. But yield is part of the research we are also working on, because we found it's critical to get the phenology to map into the crop modeling. It's especially the hard part is like they need to the planting date, they need to know the planting date in the crop growth modeling and yield estimation. That's hard information to get. It's, if you want a larger scale, you don't know actually farmers' decision, or they plant early or late. Maybe can be detect from our remote sensing the emerging state, and we can, like normally based on temperature and weather condition, we can deduct those planting date. So, and also flowering time is probably easier to detect, not near the peak VI time.
Since you are a scientist from USDA research department, Mustafa Teke from TÜBİTAK Space is asking what kind of strategy you suggest to set up a crop yield monitoring for countries like Turkey.
Okay.
Mustafa Teke.
That's probably beyond my knowledge.
Yeah. He is asking probably your personal opinion first.
Okay. If you do want to, I think the prediction for more related within season. That's kind of the when can you do the prediction? Like you have the multiple stages in early spring or and the middle spring and after. So the within season approach quite challenging is that first you need to know the crop types within season crop types. Normally those crop types are available after growing season. That's one. And second, you need to do the condition, crop growth condition, not the phenology, but also the condition compared to the historical years. And the yield, probably need to consider the technology improvement and weather condition. The model can be very complex. The strategy, I'm not involved in the large scale prediction, but mostly on the research side.
And due to climate change, we have an increasing concern about water balance management in the basins. And if you consider that more than 70% of the overall water consumption is related to agricultural operations, agricultural activities. And in order to optimize this water footprint in the agricultural side, phenological stage-based data segmentation may be more feasible than ever if we consider monitoring the precipitation, irrigation scheduling, and so on. So what is your personal opinion about the increasing feasibility rate, about better phenological or more precise, rather than it's probably better to say more precise dating for the phenological stages? How do you think about the importance, or what is the probable correlation, or what is your personal suggestion about raising importance of this issue in accordance with other types of monitoring data?
Yeah, I think that's right. It's kind of phenology. It's related to this weather condition and precipitation, water use, and also the temperature. So this is for the summer crop, cash crop we call, or winter cover crop. We also work on the rangeland actually in the Midwest U.S. We see some increase of normally the green up increase due to the precipitation. Those kind of indices. Not only like phenology metrics can be quite useful to track these changes. When normally you have precipitation and then increase of NDVI or increase in other VI indices, it's most associated with diet quality, grass quality, because it's growing quickly, you probably get a better grass quality and a better diet for the cattle, like this kind of different information. I think those information, phenology information, quite useful if you can think about a broad range of the application. It's I think that's research. That's still a research topic, especially for the near real time monitoring.
For example, in Turkey, we are in a drought season nowadays. Not only not in Turkey, most of the Mediterranean countries are affected by agricultural drought, especially this year. And Another consideration is, for example, if we have to use the KC factors, you know, the crop evapotranspiration, and the KC is not one single value, in fact. It depends on the phenological stage. So each crop has a phenological stage-based KC, so that you can compute the overall agricultural water consumption in the basin. Even though you know the pattern, crop pattern, you may not have enough accurate computation or estimation for the agricultural water usage if you are not considering the phenological stage datings, because KC KC factors severely change from one stage to another stage. And another subject of the argument here is, if we have to focus on also cases, does it merit to use them in terms of phenological stages? And will be the remote sensing based phenological stage separation or classification be enough or for feasibility of using different cases separated to the phenological stages?
Yeah, I think that's a good idea. That's a good idea to use change this KC factor. And in our lab, we work on a different way. We use a physical model to detect the evapotranspiration water use. And I want to mention there's another large activity using Google Earth Engine. It's called OpenET project. It's mapping the evapotranspiration with multiple models, physical and empirical models. They do the assembling of this model and provide the ET value for each individual field, and also at the pixel level. It's happening I think they're already done the western side of US. They are expanding the research area. KC is one of them, but they also found that phenology stage probably useful for the water use, and especially from drought time. The impact of drought to the crop yield are different from different growth stages, as we know. So if you know the crop growth stages from a large area, it probably can be used to evaluate the impact of a drought. And I like your idea, like you say, include phenology in the KC. Yeah, but I haven't studied this area. Yeah, that's very good.
And then another last question is from Mabin Akhtar, asking if there are 3 seasons of same crop in the same year, and some time of the seasons are overlapped to each other season, and crop fields are also adjacent, then how to differentiate these crops? And adding that, for example, 3 corn crop seasons before season, within the season, and after the season, but in the same year.
Okay, 3 corn crop season.
Yeah.
So we normally have a double crop, like you have winter wheat and then soybean. So is that means that you have a 3 corn in 1 year?
Yes, but as I understood, he considers that there are 3 plantations in the same field in the same year.
Is that probably related to if you want to identify different crops? Is one I think is a spatial solution is important, right? You need to identify those individual crops, not just a mix of this different crop. If it's mixed, we probably can't do much with this situation. If you can identify like right now, like 3 meter, 5 meter resolution, you can separate this, see the difference of these crops and a different time series. That probably can be separated from each other. But
it's what we also face here in Turkey. For example, while we have the winter wheat until end of June, by the beginning of May, plantation of cotton, for example, starts. And meanwhile, a month later, probably some summer crops
Yeah.
also are about to be changed. So as you have added, not only through the time series NDVI or some indices, but also using the high resolution, very high resolution, not only high resolution, very high resolution remote sensing data would be helpful. First, full classification, better classification of the crop pattern rather than the phenological stage. Then afterwards, phenological stage can be used under the context of the classified crop pattern, as well as I understand.
High spatial resolution and also high perspective from the classification if you want to.
Or they may be fused.
Yeah.
Okay.
Yeah.
Okay. Thank you for your nice presentation and this nice talk afterwards. If there is not any other question, I would like to thank all participants here, and we hope to see you in the next webinar we may have through ISAM. Dr. Fen Gao, we appreciate your presentation and thank you again.
Yeah, thank you everyone that attended this seminar.
Okay.